So, welcome back. Yeah, this is the start of the next session, and it's dedicated to post-quantum implementations. Yeah. We have 3 talks in this session. So, the first one is actually getting us to code-based implementation, and it's entitled McBits Revisited, and it's a follow-up from work from CHES 2013. It's work by Tung Chou, better known as Tony, and I think, Tony, the stage is yours.
Okay, thank you, Tim. So, I'll start with some background on code-based crypto, and specifically code-based encryption. But since that Tim and also you already saw the first talk today, some people have already talked about code-based crypto, so I think I'll just quickly go through everything. So, yeah. So in coding theory, we want to deal with this problem of sending a message through a noisy channel. So if we just send the message M directly to the receiver, then, well, maybe some error will be added to this message, and the receiver cannot get the correct message. So what we do in coding theory is that, okay, we encode the message by multiplying it with a generator matrix G to add some redundancy and to make it a code word. And then with this redundancy, so even if an error is added to the code word, later on receiver can use some decoding algorithm to recover the original message. Well, he actually get the C and E, but from C it should be easy to recover this message M. Okay, so what code-based encryption is doing is quite simple. So basically, the sender now just deliberately add an error, and then send the whole vector R to the receiver, and then again the receiver, if he want to decrypt, he can use a decoding algorithm to recover C and E. So that's how it is. Okay, so this is the general picture of the McBits scheme proposed in 1978 using binary Goppa code. Yeah, I should say this NG plus E framework is like the McBits framework. But in the paper, McBits also proposed that, okay, we should use binary Goppa code, specific code. And this combination of McBits and binary Goppa code remains secure, even, well, it's already pretty old, like 40 years old. And several years later, we also have this Niederreiter system. Well, you can consider it as a dual system of McBits. In terms of security, you can say that they are equivalent. So anyway, you can use either McBits with binary Goppa code or Niederreiter with binary Goppa code, then it should give you a pretty confidence-inspiring post-quantum encryption system. Okay. So now we can talk about what McBits is. So McBits essentially implement the scheme in the previous slide. Well, to be more specific, it actually implements Niederreiter plus binary Goppa code, this system. And the goal is to achieve fast and constant time code-based encryption. Yeah. So as a result, we actually did quite well because we managed to achieve like an order of magnitude faster speed compared to the previous non-constant time work. Okay. And the main technique we use are here, so bit slicing and some non-conventional algorithms for decoding. I'll expand this later in more detail, but what we should notice here is that the original McBits, this 2013 paper, we use external parallelism to do bit slicing. This means that we will have a high throughput. That's fine, but in terms of latency, it's not so good because we process many different instances in parallel. and we cannot get the result of one specific instance earlier. Okay. So what I do in the 2017 paper is actually quite simple. I just want to use the internal parallelism only. So as a result, this gives us a high throughput and low latency system. Yeah. So simply speaking, this is what the new McBits is doing. Okay, so now I want to elaborate more on what I mean by external and internal parallelism. Okay, so you can imagine if you want to simulate a hardware circuit, maybe like this, in software. So the simple thing you can do is you just put all the data in the first bit of your registers, and then you just do some logical operations between these registers. Eventually, you get the result, also in the first bit. But as you can see, this is wasting the computing resource quite a lot, because the remaining W-1 bits, you didn't use it at all. So the idea of bit slicing is to, just also make use of this W-1 bits. So as a result, you're essentially simulating W copies of some circuit. Okay. So as you can see, if we want to do this, there must be some parallelism, because you need to perform all this, you need to simulate all these copies at the same time. So in the 2013 paper, what we do is that we assume that there are several decryption instances at the same time, and we just make use of this parallelism. But what I do in this 2017 paper is just that, so I try to find parallelism inside one decryption or encryption instances, so that we just use this internal parallelism directly. And then we don't have to rely on this extra assumption. And the resulting system should be useful in more cases, in more applications. Yeah. Okay, let's take a look at some speeds. So from the left of this table, you see the security parameters. So yeah, here I list some numbers for pretty high classical security parameters. And as you can see, this bytes is the size of the public key. Well, this is a problem of the system exactly, because it uses a quite big public key. Okay, and on the right you see this Perl, Sing, Q, root. These are the components, the building blocks of the decoding algorithm, and I'll explain in detail later. But here you see that. And so in this 2017 paper is doing better in most of the components, but doing not so well in key equation solving. Okay, and maybe we can also take a look at the performance of the whole encryption and decryption. So yeah, so the software is taking like 300,000 cycle to 500,000 cycle for encryption and decryption, depending on which architecture you're on. And key generation is unfortunately pretty slow, but let's hope that we don't have to do this very often. Okay, so now I can talk about this component here. So basically, the decoder, we need to decode in order to decrypt. So how we actually do the decoder is like this. So the decoding algorithm starts with a single computation phase, and then we have to solve something called key equation, and this is typically solved by using the Berkham-Massey algorithm, a well-known algorithm. And then in the last stage, we do a root finding phase to find the root of some polynomial in order to recover which positions are in error. Okay, so this is the original algorithm. In the McBits paper, 2013 paper, so we try to consider things in a different way. So for root finding, as you can imagine, we can consider it as a multi-point evaluation process. If you are able to evaluate at all the field elements, then essentially you know the root of the polynomial. So okay, you can view it as multi-point evaluation. And for synchrony computation, it's a bit more technical, but essentially you can also consider it as a transposed multi-point evaluation. Okay. So what we can actually use to implement this two stage is we actually use some FFT algorithm and actually additive FFT algorithm. But in order to make use of this FFT algorithm to do multi-point evaluation, we actually encounter some problem because this FFT induce some standard order of the output, which is different from the original output we want. So what we need to do is to permute the output array of field elements. And also we have the similar problem in synchrony computation phase. So because the input order has been changed because of the FFT, so we also need to do a permutation before the transpose FFT. Okay. So this is essentially what McBits 2013 is doing in terms of algorithms being used. Okay. So in the rest of the talk, I'll just talk about how to implement these components like permutation at FFT and broken MSE. Okay. So so this is something called banished network. So the reason to use this network is to do the permutation in constant time. Okay. So no matter what your permutation is, you can use the same pattern to perform the permutation. So that's why it's nice for constant time implementation. Okay. So here you see each horizontal line is a piece of data. Well, you can consider it as a bit. And each vertical line segment is a conditional swap, which swap the endpoints depending on the condition bit C. Okay. So yeah, as you see, the pattern is pretty elegant. So you start with the stride 8 conditional swaps, and then stride 4, stride 2, stride 1, and then go back to stride 2, stride 4, stride 8. Yeah. And also, please note that given the conditional bits C, it's actually pretty easy to convert the conditional swap into a sequence, a small sequence of logical operations. We will use this for implementation later on. Okay, so now the question is how can we actually implement this efficiently in software? Okay, so now we can consider we put the pieces of data in a matrix 4x4 matrix. So if you do this, then you will notice that in stage 1, we're essentially doing some bitwise operations between the first and the third row, and also the second and the fourth row. Okay. If you keep doing this, you see, okay, also for stage 2, we're doing some operations between rows. For stage 3, situation get changed a little bit because now we're doing operations between columns. Stage 4, also columns. Stage 5, columns. Then rows. Yeah. So we have row operations at the first few stages and also the last few stages, and column operations in the middle. Okay. So so apparently you cannot just put data, store data in a row fashion way, because now you don't really know how to deal with the column operation. So, well, the naive solution is that, okay, we just do a matrix transposition between the stages where we need to do row operation and column operation. So yeah, we need to do this between stage 2 and 3, and also between 5 and 6. Yeah. Okay, so this is the idea. So, well, this is actually a very well-known technique, but yeah, I should also talk about how to actually do bit matrix transposition. So if you have a just 2 times 2 matrix, so well, transposition is quite easy. You just need to swap this 2 blocks, the right upper block and the left bottom block, and then you get the transposition of this matrix. And how about the larger cases? So if you have 4 times 4, then we also do the same first. And then we just recursively transpose each block 2 times 2 blocks like this. And then magically you have the transposition matrix at the end. Okay. So what's nice about this technique is that, for example, in this picture, if you actually want to do operations like this, if you think about it, it's actually interleaving the first and the second rows to get the resulting first and second row. And also for the third and fourth row, it's also a similar case. So you can complete all this swapping of the blocks using some logical operations between the rows of the matrix. Okay. So yeah, this is how I implement the banished network. Okay, so let's move to the additive FFT. So if you still remember, additive FFT is used for the root finding phase because we want to evaluate the polynomial at all the field elements to find the roots. Okay, so I think most people are more familiar with multiplicative case where you rewrite the input polynomial f as f0 x squared plus x times x f1 x squared. Okay. And in additive FFT, you actually do something quite similar, but you rewrite it in a different way, like this. And so the result of this difference is that in addition to the, in the multiplicative FFT case, you have a bunch of FFT butterflies to carry on. And after that, you already have the FFT results. But in the additive FFT case, you also have the butterflies. But in addition to that, you also need to carry out something called radix conversion in order to get this F0 and F1. And later on, we'll see the computation pattern for this. Yeah. Okay. So yeah, now we have the butterflies like this. So yeah, I draw it as a vertical line segments instead of the usual butterfly picture, but I think you can understand the meaning. So if we have a full FFT, which means that the length of the input polynomial is full. It's the same as the number of evaluation points. Then the picture of butterflies is essentially like this. So as you can see, this is very similar to the, well, not similar, it's essentially the same as the second half of the banished network. So because of this, we can actually implement it using the same technique. We can do some transposition here, and then we should be fine. We can do operations between the rows of the matrix. Okay, but actually the situation is a bit nicer, actually, because of our parameters. So in our case, we actually have a low degree input for the FFT. So to give you the actual numbers, so the polynomials in the 2013 paper have length 128, but the number of evaluation points is like 2 to the 13. Okay, so because of this, we can actually get rid of some of the first stages And as you see in this picture, if the picture is exactly like this, then we don't have to use transposition at all. Yeah. The actual situation is pretty similar to this, but it's just a bit different. So we need to take a bit more operations to compensate with the a few extra stages. Yeah. But essentially, this is what we have to do. We don't have to carry out the whole transposition. Okay, and now we can talk about the things in addition to butterflies that we need to carry out in additive FT. So in order to get to rewrite the polynomial f in F1 and F0 and F1, what we need to do is some operation like this. So we divide the polynomial into 4 pieces. And then we add the third piece, the fourth pieces into the third piece, and then the third piece into the second piece. Okay. And then we do this recursively. So we do this for the second half, and for the first half, and for the second half. And also we need to do some scaling in order to multiply the whole polynomial by some small constant. And we just repeat this all the time. Okay. So as you can see, the operations for radix conversion is quite regular. So we can actually do this with some logical operations. And for multiplication, this multiplication, we can do it with a big slice multiplication because we can process all the field elements in parallel. Okay. And also because the degree of the polynomial is quite low, so this is actually quite cheap compared to the butterfly part. Okay. So I think I don't have much remaining time, but I want to quickly go through key generation. So basically for public key generation and also secret key generation, you can consider it as some Gaussian elimination process. And actually, in both cases, it's pretty easy to perform the Gaussian elimination in constant time. And we already showed this in the 2013 paper. But actually, we implemented in the 2017 paper. Okay, so I don't have much time, but later on, you will see the third talk of this session. They will talk more about key generation. Okay, so that's very quick, going through my work this year. So I put everything in this website, including the paper and also the source code, also explanation of the software. So if you feel interested in this work, you can go here and maybe download the software and play with it. If you have any question, I'm very welcome. Just write email to me. And yeah. So yeah, that's all for my talk. Thank you very much.
Thanks, Tony. So we have time for one quick question. Any questions? Over there.
Hello, sorry, could you just say a few words regarding the presentation that we had this morning on sidechain attacks on such implementations, if the attack that was presented earlier applies also to this version of McBits? Thank you. There was a DPA attack basically on another...
You mean the attack in the first talk today? Or?
Yes, yes.
Oh, okay. Yeah, I cannot really comment on this because, well, both QuickBits and McBits are for being constant time. Yeah, I didn't consider attacks like side channel power analysis, that kind of attack. So what will happen? Well, I didn't consider this. Yeah.
Okay, so let's thank Tony again. Thanks. So now we're getting over to lattice-based crypto. Yeah. The next talk is titled High-Speed Key Encapsulation from NTRU. It is joint work by Andreas Hülsing, Joost Rijneveld, John Schanck, and Peter Schwabe. And Joost is giving the talk. Please.
Thanks for the introduction. Oh, the mic. Yeah. Got one. Yeah. Thanks for the introduction. Yeah. So my talk is going to be about high-speed key encapsulation from NTRU. Joint work with Tim just listed everybody. So what is the problem here? We're looking at doing a key exchange. So we want to securely exchange a key, and this is in a context where the adversary has a quantum computer. So that changes a bit how you're looking at things, but in general, just assume we're doing key exchange. There have been a lot of proposals trying to fix this problem, and a lot of them are lattice-based. This seems to be the direction that many people are moving to. You might have heard some of these names: New Hope, Frodo. Well, they're all on the slide. And typically these papers and these works come with real-world implementations and or parameters and actual implementations that work and are fast enough to work in practice. So this is a very promising field of work that is actually usable. But in this talk, I'm going to go back to the basics. I'm going to talk about NTRU, which is a system that was designed almost 20 years ago. And I'm going to show how this is also usable. As some of you might know, the patents for this have expired or have recently been set to expire, but were released in March already. And I'm going to talk about how you can now actually use NTRU, make it a bit faster than the original proposal, make it a bit more secure. Well, let's show parameters. So this talk is basically split into two parts. I'm going to talk about parameter choices. How does NTRU work? Which parameters did we select? And then I'm going to discuss implementation details, because I mean it's CHES. I'm going to focus on polynomial multiplication and on inversion, and give you an intuition why this is fast and constant time. I'm not going to do a bunch of other things. This is all in the paper, so if you're interested in reading about the sampler or more context about NTRU, how we came to these parameters in more details, some of these other context things, read the paper. I'm not going to go into all these details here. Let's get started. So there's basically three parameters that we need to concern ourselves with. There's n, there's p, and there's q. And these are familiar for any NTRU-based system. And just get it over with, I'll assign numbers to them. We pick n is 701, p is 3, and q is 8192. So a nice power of 2 for q, a prime for n, and a small prime for p. And we're working over a ring. And this ring is the ring that you commonly see in NTRU systems. It's polynomials over x to the power n minus 1. So polynomials of degree n, that's the intuition that you need to have for the rest of this talk. But we're not just working on this ring, we're working on a different ring as well. There's a ring S, and it's defined over the nth cyclotomic polynomial. And the crucial part here is the relation between, let me see if the pointer works. Yeah, so there's a relation between the ring R and the ring S, and it's this multiplication by x to the power, or multiplication by x minus 1. And essentially what this allows us to do is to do our computations in R, while we benefit from the security of actually working, well, not actually in S, but the system is based as if we were working in S. And this provides some countermeasures against common faults or common security problems that people exploit when you're just working in R. This has to do with this factor x minus 1 that is present in R but no longer in S. But yeah, this relation allows us to still do fast computation. I'll go into some more detail in a bit. But if we look at how NTRU works, this is basically NTRU in a nutshell. We sample some F and some G, and we sample them from S here. And then we lift them to R. This is the conversion again. And for the private key, we basically have this F, which is a polynomial of some coefficients mod 3. And the public key is some expression over the lifted polynomials. And you'll see that we're now performing operations in R here. So that's a multiplication and an inversion and a multiplication by some constant polynomial to derive the public key. And then encryption and decryption work as follows. Basically, it's a couple multiplications in R. Here are some multiplications in R, then a multiplication in S, and this inversion in S. But this inversion you can actually also do during key generation, because F is something you know during key generation, so you don't actually need to do this inversion in real time. You can have this pre-computed. So basically, you're doing a couple multiplications for encryption and decryption. That's essentially how it works. How do we come to these parameters? Basically, this summarizes the parameters again. The core here is that we don't want any decryption failures. We wanted to go for a very simple system, and the crucial part here is no decryption failures, while still making it easy to sample F and G, and making it easy to sample R and M. So R is this randomization thing that you saw here in the encryption phase. M is the message that we want to send. And F and G is what we sample during key generation. We wanted to keep everything as simple as possible, and this implied, well, no decryption failures during your encryption-decryption procedure. How did we achieve this? So a crucial part here is that we have this factor x minus 1 again. It's now an explicit factor in the public key. And this allows us to also not worry about sampling F and G with any fixed Hamming weight, because typically in these systems you would see some things like you need this many bits to be 1 or 0 in F and G. We also get rid of this requirement here, which means that we don't need to do any rejection sampling on F and G. We just pick them randomly. Well, modulo some small condition, but in general you basically pick them randomly, and that works. Similarly, because this n is 701, it's irreducible mod 3 and q. This means that F is, there's some reason for this, I'm not going to go into the details here, but the conclusion is that F is always invertible. So also you don't need to worry about picking invertible F, no invertibility tests, which also makes it very easy to do this in constant time. All in all, this makes this parameter set straightforward to implement in a constant time way, especially during key generation, which is the crucial part here. Since we're doing a CAM. On the subject of doing a CAM, so basically what we're doing is we're using a CPA secure system and then transforming that into a CCA2 secure system in the quantum random oracle model. The intuition here is that we're just adding some randomization, some hashes here and there, and relying on the encryption and decryption routines to come up with encapsulation, decapsulation to, well, exchange the symmetric key that can then, well, basically the message is a symmetric key that you then use as a result of your key exchange. The takeaway is it requires a couple soft calls. We use Shake for this. Some additional data, but in general, this is a relatively straightforward operation. It adds 140 bytes to your ciphertext, which is like 10%, we'll see in the end. But yeah, that gives you a QROM proof for the CAM. So we've seen some operations during key generation and encryption. We need to sample some stuff from S, so F and G and the randomness and M. And there's a bunch of polynomial arithmetic. We're doing multiplications in R, multiplications in S, and inversions in both of those fields. Most of this happens during key generation, especially the inversions. You don't need to worry about those online. But if you're doing some ephemeral CAM, still key generation is very relevant. So that's why we're also focusing on these a lot. And then there's some arithmetic on the side. We need to lift from this small ring to the larger ring and do some modulo arithmetic around it to do these conversions. But I'm going to focus on these two operations, multiplication in R, inversion in R. The other two are very similar and less interesting to talk about, but you can read about them in the paper. For now, I'll focus on these two. The target platform that we implemented this on is an Intel Haswell, so large Intel. And we heavily rely on the AVX2 instruction set, vector instructions. So the first, we're going to do multiplication in R. And for those of you who don't really recall what R was again, basically picture it as polynomials with 101 or 701 coefficients. And all the polynomials are mod 2 to the 13. So these are nice binary coefficients. Or well, not binary, but to some power of 2. And this means that they fit nicely in vector registers. Because these are 2 to the 13, they fit nicely in 16-bit words in a vector register. And we're going to do some multiplication routines to make this multiplication a bit more easy to deal with. we're going to use Tung Chou and Karatsuba. Karatsuba is probably well known here. For those of you not very familiar with it, Tung Chou works similarly. You have a large multiplication that you reduce into smaller parts, rather than using a schoolbook multiplication where it scales quadratically. It goes a little bit less than quadratically. Karatsuba goes from 4 to 3, while Tung Chou goes from 9 to 5, for example, or larger tungs go from have a slightly different factor. We're going to rely on dimensions as close to 16 as we can, because we have these 16-bit words in 16 of them in a register. So if we can get dimensions into nice factors of 16, everything becomes very efficient. You can do nice multiplications. We'll see that in a bit. So we're just going to go through this. Start off with Tung Chou. We're doing Tung 4, which means that we have 4 limbs. We cut our polynomials into 4 pieces. That would imply 16 schoolbook multiplications, but if you're doing Tung 4, that means 7 multiplications of, well, 176 coefficients. And we split this further using Karatsuba, and we split this once more using Karatsuba. And now we have polynomials of 44 coefficients, which is almost 48. And we have 63 multiplications, which is almost 64. And this is the crucial part. Now we transpose these. And rather than putting our polynomials in vector registers, we now put all of these polynomials in parallel into these registers. And now we can do all these multiplications at once. Add a few more layers of Karatsuba, schoolbook registers, and schoolbook multiplication in the end. And this allows for very fast multiplication of these seemingly large polynomials. In the end, we only need around 12,000 cycles. Roughly half of this is the actual multiplication. There's some cost in doing the transposition and doing the interpolation steps in Tung and Karatsuba. But yeah, this is a very fast routine for doing these multiplications. This multiplication is one of the crucial parts in your encryption routine. So to get this fast, this is very crucial to get a fast encryption. So that's one part of the building blocks. Next, inversion. And inversion is a bit more tricky. You'll see you in a bit. But the context is the same now. We have, again, polynomials of 701 coefficients in R. And we're first going to break this down a bit. We're doing Newton iteration to break these polynomials down from RQ to R2. Now, R2 is a much nicer field, because then you have binary polynomials. And Newton iteration is a algorithm that was proposed almost 20 years ago as well. In one of the NTRU tech reports. There's a bunch of these tech reports where Silverman et al. Propose ways to implement NTRU. One of them suggests, well, doing the scaling. So we're doing 8 multiplications in RQ, which we just saw we can do pretty fast, to scale from R2 to RQ when we're doing inversions. So now the new problem is we need to do an inversion in R2. Now the coefficients are binary. We still have 701 of them. But yeah, the problem is greatly reduced at the cost of a bunch of multiplications. So how do we do this inversion in R2? Well, we have a look at Fermat's little theorem. And this is a well-known result, I guess. Then we apply an algorithm called Ito-Tsui's inversion. By finding an addition chain, you can combine multiplications and multi-squarings to do this large exponentiation. And essentially, this gives us the inverse. If we now combine these multiplications and multi-squarings, we can get to this 2 to the power 700 minus 2. So now we have 2 new subgoals. Subgoals are we need to multiply polynomials, again, multiplication, and perform multi-squarings. Multi-squarings, well, we'll see that in a bit. So first focus on the multiplication. As we saw before, multiplication, we can do a composition of Karatsuba and Tung Chou. But in this case, Intel provides us with some very nice instructions. There's the CL-mul instruction set, which allows you to do multiplications in binary polynomials. There's the VPCL-mul QDQ instruction, which multiplies polynomials of 64 coefficients. Well, we don't really have them yet. We have 701, but we can do a similar trick as we did before to reduce these polynomials to a nice dimension where we have 64 coefficients. We apply some Karatsuba, in this case degree 3 Karatsuba, because I mean it's a bit of a trial and error to find a nice way to reduce these polynomials without introducing a lot of costs doing interpolation and evaluation steps. In this case, the three-Karatsuba works nicely. Then we add another layer of Karatsuba, and we have polynomials of 117 coefficients, and break it down again. And then we're pretty close to 64 coefficients. We can apply the CLMO instruction set and get to only 244 cycles per one of these multiplications. And you can do all of this in registers. Because of these large vector registers, you don't even need to swap anything to memory. These polynomials fit into a couple of them. You only need very little temporary data. And if you do this carefully, you can keep everything in registers while you're doing this computation. So that's another sub-goal. And now we still have the multi-squaring left open. And we need to analyze this a bit, see what this actually is. Because if you think about it, it's actually about permuting bits. So you're not doing some arithmetic, but you're basically shuffling bits around. And if you think of the problem as permuting bits, it suddenly becomes a whole different problem, and there's a whole different range of solutions to it. I'll quickly walk you through an example. If we have a look at a binary polynomial, we do it mod to, x to the 7 minus 1, which is easier to look at than x to the 701 minus 1. Let's have a look. For example, we take this random polynomial, represent it as bits, and then if we square it, we get this beast. But now I've left in all the binary, or well, the coefficients that would reduce in set over 2. So if I leave those out again, I get this polynomial. And basically, if you look at the binary representation, oh, where's my pointer? Anyway, if you look at the binary representation, you now see that it's basically the same thing, but then expanded. There are zeros in between, because all the terms basically shift a bit to the left. And this sort of gives you the intuition that we're going to just move around bits. Because if we now reduce mod this x to the power 7 minus 1, what we do is we take the top part, we shift it to the right and add it back. The shifting to the right is because of the x to the power 7, the adding it back because of the minus 1. And then what you see happening is that basically the set bits from the top part fall into the unset bits places of the bottom part. You can add them back in together, and you basically get this result. And this is a permutation on the bits of the original polynomial. And the crucial part is that you can compose these. We're not just doing one squaring, this is just doing one squaring, but we're doing multi-squaring. So, for example, 2 to the power 300 would be one of these squarings, not just to the power 2, but to some exponent of 2. And these are just a composition of permutations. If you're doing one permutation, you might as well do a bunch of permutation, and it's still a permutation on the bits. So we've now changed the problem to only solving permutations on these vectors, and then we can do arbitrary multi-squarings. And if we now look at how to do these permutations, we can do it in 2 ways. We can either write dedicated routines, so look at each individual permutation that we need, like which exponent do we need, how do we need to permute the bits, or we can generate assembly in general, like write a routine to tackle this problem. And so we opted for the second option. We first tried the first, but it proved to be pretty tedious. And I'll show that this is not actually that much worse in terms of performance. So what we did is we wrote a Python tool that can simulate a subset of the relevant AVX2 instructions. So typically you would need XORs and ANDs and masks and those kind of things. But there's a whole lot of instructions that are completely irrelevant for permutation, so we leave those out. But we now have this subset of AVX2 that we can interactively use instructions of and then see what this does to the permutation of bits. And rather than having a look at the output, which is just a series of 1s and 0s, you can then tag the bits with their initial position and the goal position and sort of track where they're going. And then interactively create these routines. So this allows you to write individual routines for the permutations that you need. Or it allows you to write generated assembly, or routines that generate the assembly. We basically have 2 options to do this, 2 approaches. And one of them uses bit extraction routines. Bit extraction instructions, so that is based on a variant of patient sort where we're looking for subsets in the input. So you have 64-bit inputs to these instructions. Some of the bits are relevant, some of them are not relevant. By marking the ones you need, you can sort of find efficient ways to group them together, extract them, insert them into different output blocks or output quad words. And this is very efficient, especially if you have sequences of bits that are sort of ordered. Like if you're doing a permutation that interleaves them one by one, you could first extract all the odd ones, then extract all the even ones. So very structured permutations, this performs very well. On more random permutations, it's not as great. And then we use combinations of shuffle bytes and permute quad words. And this performs well on more random permutations. Then you can apply arbitrary masks and extract permutations by the byte and extract bits by the byte and shuffle them around in a way that you get to the same permutations. These routines give us single squarings in 58 cycles. This was a hand-optimized routine. If you want to do a single squaring, it's nice to like really carefully do all of them. And multi-squarings in 200 cycles and a bit. So this gives us another block. So for the inversion, we now have all the blocks together. We have these multiplications and inversions. These break apart into multiplications and multi-squarings, which are exactly multiplications and bit permutations, which add up to the following cycle count. So multiplications were 11,000. The inversion in R2 is about 10,000. So that gives us a total of about 100,000 cycles for this inversion in RQ, because we do this multiplication 8 times. That's basically the main cost. And this inversion in R2 is pretty cheap. So quickly get to some results. Encapsulation now only takes just below 50,000 cycles. Basically, that's mostly multiplication and then some stuff around it. You need to do shake a couple times, conversion, sampling. And decapsulation is very similar. You rely on the encryption routine from encapsulation, so that's the multiplication. Do a couple more multiplications. Well, only 60,000 cycles as well, or almost 70,000, but still. But the most crucial part here is key generation. Because we can now use these fast inversions to, well, I haven't shown the inversion in S, but it's also pretty okay. We can now use these fast inversions to do fast key generation. And this is crucial if we want to do NTRU in a CAM. If you're doing an ephemeral CAM, you would need to do key generation online as well, not just the first two routines. Well, we run these benchmarks on a large Haswell, as I mentioned before. This comes down to 1/10 of a millisecond or 0.02 milliseconds for encapsulation and decapsulation. But again, key generation is key here. So brief comparison. I'm not going to go into details because there's a lot of footnotes here. For most of these, there's either some very optimized implementation, some C implementation. Some of these benchmarks were not even listed on papers and were listed by other people or in Supercop. So there's a bunch of footnotes here, but to give you a general idea, NTRU CAM is in the same order of magnitude as most of these for encryption and decapsulation, but especially fast in key generation, and similar in size, pretty small, as you're used to with lattice-based key exchange. So yeah, this puts it into context a bit. But the takeaway is this. Key generation can be fast, it can be easy, there's no need for decryption failures. Everything can be constant time, even in a CCA2 secure CAM context. So yeah, that wraps it up in terms of what you would need to do for NTRU. Code is available, everything is public domain. The bit permutation tool that we wrote is, we put it online as a separate tool, so you can also use it if you want bit permutations in a different context. Yeah, so please have a look if you're interested. Thanks for your attention.
Thanks, Joost, for the talk. We have time for 1 or 2 questions. So I have 2. Actually, with NTRU becoming patent-free, yeah, do you consider this as a submission for the NIST call?
Well, I haven't personally considered it, but I can imagine that there's people out there that are sufficiently interested in NTRU now. Yeah. Especially since, of course, it's seen 20 years of non-breakage. There might have been a lack of focus because of the patents a bit, but yeah, it sounds like a very conservative way compared to other key exchanges out there.
Okay, and there's a follow-up question on that. Since when you look at the NIST specification for the core, they say they want to have non-optimized reference implementations. What would be the penalty if you take out all the AVX assembly stuff? What is in the...
So it's hard to say, especially for the inversion in R2 that's very focused on AVX2 assembly. we have a reference implementation in C where we're doing a different way of doing this inversion, then we're using this almost inverse algorithm, which is, I mean, the intuition is sort of similar to extended Euclidean, but then we're also doing this in a constant time way. So there's ways to do this relatively fast, but of course there's going to be a penalty. I mean, it's not prohibitively much slower. I don't have the exact numbers, but it's an order of magnitude. But yeah,
I believe that. Yeah.
Yeah.
Okay, many thanks. So we're now getting back to the last talk in this session, and also a talk from the code-based cryptography, and it's entitled FPGA-based key generator for the Niederreiter cryptosystem using binary Goppa codes, and it's joint work by Wang, Jakub, Szefer, and Ruben Niederhagen, and Wang is giving the talk. Please.
Okay, so thank you for the introduction. I'm Wang from Yale, and my advisor is Jakub Szefer, also from Yale. And this is joint work with my collaborator from Fraunhofer Institute SIT in Germany. So I'm here to present our work, which is a hardware version for the key generator of the Niederreiter crypto system, which uses binary Goppa codes. So just a brief background for the code-based cryptography. So due to the arrival of the big enough quantum computers, nowadays, the post-quantum cryptography can be divided into two classes. The classic cryptography, which we're using nowadays, and the post-quantum cryptography. And for public key encryption, we have a few candidates. Among them, lattice-based and code-based are the most popular ones. So we pick code-based for our implementation because it's the most confidence-inspiring scheme. And originally, McLeese proposed this McLeese code-based scheme in 1978, and several years after that, Niederreiter proposed a variant of it, which actually introduced a trick to reduce the public key size. And also, Niederreiter has a more efficient decoding algorithm. And in the very original proposal, Niederreiter used the generalized Reed-Solomon code, which has been broken. And later, the efforts with binary Goppa code, they remain secure nowadays. And more recently, people tried to introduce some structures into the code, for example, some QCMD-PC code, but there have been attacks on these schemes. So in our implementation, we focus on a binary Goppa code-based Niederreiter crypto system. And now let's get some motivation for why we are implementing a huge key generator in our hardware. So we know that for public encryption scheme, we have 3 modules. First, we need a key generator to generate the pair of keys. And for code-based crypto system, as far as we know, there has been no existing hardware implementation which provides such high security levels. And I will talk about why we are targeting at this security level pretty soon. And this module actually is very complex, both in logic and in cycles. And that's the reason why there is only one existing work that included this module in hardware. But at the same time, the hardware implementation is needed. For example, if we want to implement some hardware security modules or some cryptographic smart cards and etc., all of these applications, they actually need dedicated key generator modules. And for code-based, the encryption is very cheap. It basically can be mapped to a matrix vector multiplication, which can be applied by a bunch of XOR operations, which is very cheap in hardware. And the decryption part is actually more interesting, and that's why there are quite a few works that have been done on both encryption and decryption. Therefore, in our work, we are targeting at implementing an efficient key generator for the code-based crypto system. And I just talked about the 266-bit security level that we are targeting. Actually, this comes from the recommendation from the PQ Crypto project, which was published in 2015. And such high security levels, they correspond to this set of system parameters. First is the field size, which is a binary field. In our scheme, m equals to 13. And then you need to determine the number of errors that you are able to correct, which is t equals to 119. And then there's a code length, which is the length of your message, which is 6,960. And this set of system parameters, they correspond to our 1 megabyte public key, and that's also the main reason that this set of parameters were proposed. And also a secret key, which is around size 13 kilobytes. And as you can see, 1 megabyte is pretty large for hardware. Therefore, implementing an efficient key-generating hardware is a challenging topic. So to give you a better idea of what this security level means, I compared it with a few related work. So there is one existing work which included the key generation, also in their design, which was published in 2010. But you can see that the security level they provided is only 103, while our work actually provided a 263-bit classical security level. So this security level can be somehow converted into the post-quantum security level, which is well above 128-bit, actually. And the other related work, they only implemented encryption, decryption. Okay, so before talking about the actual algorithms that we used, I'd like to give some coding theory background. So we have been talking about binary Goppa code. So how do we actually define a binary Goppa code? So we need two parts to determine the code. The first is a Goppa polynomial, which is of degree t. And then we need to pick the code locator, which contains n distinct elements. And you need to make sure that the evaluation of the polynomial at all these elements within this code locator are non-zero. And then how do you define the code word? You can define it by calculating a parity check matrix, which is labeled as H here. And later you will show you will see the format of this matrix. So when given a random vector C, you only need to check whether the matrix vector product between H and C equals to 0 or not. If this is the case, then you can see it's a valid code word. So we know that if we know the Goppa polynomial and we know the code locator, we can uniquely define our binary Goppa code. So these two parts, they should be kept secret, which would be later published as the secret key. And H here will be published as the public key, which will be used to encrypt your error message within this encryption procedure. And after encryption, you simply publish the syndrome as your ciphertext. And decryption module basically means you need to recover your error message out of the given syndrome. So next, I will show the algorithm that we used for our implementation. So first, you need to pick the system parameters, the field size, number of errors, and the code length. And then you need to first determine your code locator, which contains n distinct elements. And then you need to determine your Goppa polynomial, which needs to satisfy the requirement that the evaluation of the polynomial at all these points within the code locator are non-zero. And then you start calculating the parity check matrix, which is H. So H looks like this. And then you transform the matrix into its binary format, which is easy to achieve because you're working in hardware. And then you apply a matrix systemization on this parity check matrix. And then finally, you would publish the right side of the systematic form of the result at the public key, and the Goppa polynomial and the code locator as the private key. So if you go through the algorithm, you can see that we need 3 main modules to finish the computation. So first, you need a module to generate the random sequence, which is a code locator. And then you need a module to do the polynomial evaluation, which is needed for calculating the parity check matrix. And in our implementation, we applied the minimal polynomial trick to generate the Goppa polynomial GX, which we actually got the coefficients by solving a set of linear equations. So, and also, you can see we need to do matrix eliminations on the parity check matrix, and either solving systems of linear equations or matrix systemizations can be implemented by our Gaussian systemizer. So next, I will start introducing the 3 modules that we implemented. So first is a Gaussian systemizer, which can be used to solve systems of linear equations or matrix systemizations. So generally, people use Gaussian elimination, which I think you will know more or less about this algorithm. So how does it work? Now let's say we are given a matrix. In hardware, you can simply build a systolic architecture, which looks like this. And then what you do is you just feed the matrix from the top of the architecture, and then the output from the architecture will give you the eliminated format. So this architecture here works perfectly for small matrices, but not for large matrices. Because we know that we need to build an architecture which is of the same size as the matrix size. However, eliminating huge matrices is actually needed for code-based systems because of the large parameters. Then how do we do it? The only previous work that also implemented Gaussian systemizer, they achieved it in this way. So instead of having a huge systolic architecture, which is of the same size as the matrix, you can develop 2 systolic architectures, a triangular one and a square one, and then use them to simulate the functionality of the original huge architecture. And in their implementation, they divided the elimination into 2 phases. First, you do a forward elimination, which transforms the left side of the matrix into an upper triangular formula. And then you revert this forward process, which means you do a backward elimination. And then the left side of the matrix is fully eliminated. And then all you need is to keep the right side of the elimination result. So instead of applying these 2 phases, in our implementation, we combined the forward and the backward elimination. Therefore, we only need 1 phase to finish the whole elimination, which saved us a lot of cycles. And we also optimized the logic by combining these 2 architecture into 1. So now we only need 1 square processor architecture. You can either configure your diagonal processors as processor A, which are the special processors, or as general processors, which is processor B here, depending on your needs. And then again, you can just feed your matrix from the top of the architecture. And then from the bottom of your architecture, you simply get the eliminated result. And also the special processors, which are the diagonal processors, they would produce some operational codes, which would be passed to the right side of the architecture. And then how does this architecture work for huge matrices? So we developed such an interface. So let's say, what we can do is we can divide the huge matrix into smaller column blocks. And the size of the column block equals to the size of the architecture that you want to build. And then you store the column blocks into a piece of memory. And then you just start feeding the first column block into the small architecture. And then you record the data out, write them back to the memory. And then you keep doing this for the second column block, and you repeatedly do this until you eliminate the whole matrix. So by introducing such an interface, we're able to achieve elimination for any large-sized matrices. And here we show some performance for our GF2 Gaussian system method, which works for such a huge-sized matrix, which actually corresponds to the size of the parity check matrix. And you can see here that you can easily achieve a trade-off between timing and logic by tuning the size of the architecture. And the number labeled as blue shows the best time area products configuration. And since our Gaussian system method is fully parameterized for field size and for matrix size, you can simply pick your field size and your matrix size and then synthesize it for your design. And here, this table shows the performance for the GF2 to the 13 Gaussian system method, which is used to get the Goppa polynomial, which I would explain later. And during the first talk, Tony already gave some background about additive FFT. So additive FFT, we also used it to do multi-point polynomial evaluation. In hardware, the most conventional algorithm that people use is Horner scheme or chain search, which follows a similar patterns. You simply do a multiplication, then addition in a nested way. If you want to do evaluation at multiple points, you just simply scale either your cycles or your logic linearly. So instead of applying this idea for additive FFT, it actually does polynomial evaluation at multiple points at the same time. And the key step is the radius conversion, which converts your polynomial into two half-degree polynomials. You can simply achieve it by some by some linear operations. And then once you represent your polynomial in such a form, you can see the evaluation of the polynomial at a point alpha can be easily represented like this. And since we're working in a binary field, so this equation holds, because 2 times something, we're just disappearing a binary field. And then we can see that the evaluation of the polynomial at point alpha plus 1 can be easily calculated if we already know f alpha. We only need one extra addition operation, which is very cheap in hardware. So by this stage, we can see that the polynomial evaluation, if we want to evaluate the polynomial at all the points in field GF2 to the m, we actually only need to evaluate the polynomial at half of the points, and the rest half of the results can be easily calculated by some cheap operations. So what we can do is we can further apply this process to these half-degree polynomials, f0 and f1, to achieve even much less cycles. But before doing that, you need to make sure that you have an element 1 in your new basis, because you want to apply the alpha plus 1 and alpha trick again and again. So before each radius conversion, you need a twisting operation, which basically maps to some polynomial twisting operation. And you can recursively do this in software until you get a bunch of constants. And then you start the reduction, which I think this is equivalent to the butterfly process in Tony's presentation. So how do you actually do it in hardware? So in software, we can easily do it in a recursive way, but that's not the case for hardware, because recursive implementations is very expensive. So we provided a non-recursive hardware implementation for additive FFT. So once given the Goppa polynomial, you first feed it into the twisting module, which maps to a vector scaling operation. And then you feed the twisted polynomial into the radius conversion module, which transforms the polynomial into two half-degree polynomials. And then you repeat this process for some rounds or for some levels until you get a bunch of constants. And then you feed it into the reduction module. So within the reduction module, you have two pieces of memory. The first is data memory, which stores the temporary computational results, and the constant memory, which stores the points that you need to evaluate during each level. And here we showed some performance data for our additive FFT. There is one parameter that you can tune, which is the number of multipliers you want to apply in your twisting module. And for the configurations, you can see that we only need around 1,000 cycles to finish the evaluation for degree 119 polynomial at 2 to the 13 points. And we also compared our design with the Honor implementation, and you can see that we achieved a much smaller time area product compared to Honor. We also implemented a permutation module, which is used to generate the random code locator. So the idea basically is you first initialize an array with an ordered list. Okay. And then you generate valid indices, and then you do the swapping, and you go through the whole array, and finally you get a shuffled array. And this part actually is very easy to implement, and you can see that it's also very cheap in hardware. So now let's take a look at how we actually combined these modules to generate our secret key and public key. So first, we used the Fisher-S shuffle to generate the code locator. And then we used the minimal polynomial method, which got all the coefficients by solving linear equations. And we used the GF2 to the 13 Gaussian system method for doing this. And for public key generation, we used additive FFT to calculate the evaluations, and then we calculate parity check matrix. And following that, we eliminated it. And then finally, we would publish the P memory contents and the R memory contents as the private key, and the right side of the systematic form as a public key. So this table shows some of the performance results for our key generator. So you can either target as minimizing your logic or targeting at high performances. You can simply pick your design parameters freely. And since our design is not FPGA specific, we also provided some performance data for the Xilinx performance. And we also try to compare our design with some existing work. So we first synthesized our design with the system parameters that was used in the 2010 paper. And we can see that we need much less cycles while maintaining a good frequency. And finally, we need less time compared to their design. So I didn't compare logic here because they didn't provide much detail in their paper. So I also compared my design with Tony's work, which he just presented. And as you can see, although our FPGA runs at a much lower frequency, since we need much less cycles, finally we can actually find that our FPGA design is very competitive, even comparing with the fastest C implementation. So to conclude, we built 3 modules: Gaussian system method, additive FFT, and Fisher-S shuffle. And by combining these modules, we successfully generated secret key and public key. And we provided our design, which provides 266-bit security level, which is able to generate key pairs within 3.5 times 3.7 milliseconds. And our code is made public. You can access it through our lab webpage. Thank you.
Thanks, Sven, for the talk. Are there any questions? We have time for 1 or 2 questions. Everybody's hungry, waiting for lunch. At least I have a question. I think it's the first hardware implementation for the 266 security level. And so it would be very interesting to see the full package. What would be your expectation if you consider not only key generation, but also the full core, including encryption and decryption? What will be the costs?
Actually, key generation is the most expensive module. And now we actually already have a complete crypto system. And I think pretty soon we are able to provide the performance data for the whole crypto system. But encryption and decryption, they are much cheaper, both in logic and cycles, depending on our preliminary results.
The full design becomes also public?
Well, yeah, soon.
Okay, yeah. Any further questions? So let's thank all the speakers of this session again. Before you rush out to grab some of the delicious lunch the general chairs has provided for us, I'd like to make a short announcement. If you like to watch yourself, or maybe also the talks in live stream, you can go to the website. It should be online there. Yeah? So, and now, enjoy the lunch.